Randomized weighted majority algorithm. Although randomized greedy achieved a significant performance gain compared to the greedy algorithm, we still have a logarithmic ratio to the best action. Looking more closely at the proof, one can see that the losses are greatest when the sets s to the t are small, since the online loss can be viewed as proportional to 1 over the size of s to the t. One way to overcome this weakness is to give some weight to actions which are currently near best. That is, we would like the probability mass on some action to decay gracefully with its distance to optimality. This is the idea of the randomized weighted majority algorithm of Littlestone and Wormuth. Specifically, in the randomized weighted majority algorithm, we give an action I whose total loss so far is Li, a weight Wi equals to 1 minus tau to the Li, and then choose probabilities proportional to the weights. Pi equals to Wi over the summations of Wj summing for all j starting from 1 to n. The parameter tau will be set to optimize certain trade-offs, but conceptually think of it as a small constant, say 0.01. In this section, we will again assume losses in a set either 0 or 1, rather than within the closed interval between 0 and 1, because it allows for an especially intuitive interpretation of the proof, theorem 4.5. We then relaxed this assumption in the next section, theorem 4.6. Randomized weighted majority algorithm, RWN. Initially, Wi to the 1 equals to 1 and Pi to the 1 equals to 1 over n for I in X. At time t, if Li to the t minus 1 equals to 1, let Wi to the t equals to Wi to the t minus 1 times 1 minus tau. Else, Li to the t minus 1 equals to 0. Let Wi to the t equals to Wi to the t minus 1. Let Pi to the t equals to Wi to the t over capital W to the t, where capital W to the t equals to the summations of Wi to the t, summing for all those I in X. Algorithm RWN and theorem 4.5 can be generalized to losses in the closed interval between 0 and 1 by replacing the update rule with Wi to the t equals to Wi to the t minus 1 times 1 minus tau to the Li to the t minus 1. See exercise 4.3. Theorem 4.5. For tau less than or equals to 1/2, the loss of randomized weighted majority RWN on any sequence of binary chosen between the set 0 or 1 losses satisfies L RWN to the t is less than or equals to 1 plus tau times L mean to the t plus ln n over tau. Setting tau equals to the minima chosen between the square root of ln n over t and 1/2 yields that LRWM to the t is less than or equals to L mean to the t plus 2 times square root of t times ln n. Note, the second part of the theorem assumes t is known in advance. If t is unknown, then a guess and double approach can be used to set tau with just a constant factor loss in regret. In fact, one can achieve the potentially better bound L RWM to the t less than or equals to L mean to the t plus 2 times square root of L mean times ln n by setting tau equals to the minima chosen between the square root of ln n over L mean and 1/2. Proof. The key to the proof is to consider the total weight, capital W to the t, what we will show is that anytime the online algorithm has significant expected loss, the total weight must drop substantially. We will then combine this with the fact that capital W to the t plus 1 is greater than equals to the maxima of Wi to the t plus 1, where the maxima is chosen between I, which is equals to 1 minus tau times 1 minus tau to the L mean to the t to achieve the desired bound. Specifically, let f to the t equals to the summations of Wi to the t summing for all those I such that Li to the t equals to 1 over capital W to the t denote the fraction of the weight capital W to the t, that is, on actions that experience a loss of 1 at time t. So, f to the t equals the expected loss of algorithm RWM at time t. Now each of the actions experiencing a loss of 1 has its weight multiplied by 1 minus tau, while the rest are unchanged. Therefore, W to the t plus 1 equals to W to the t minus tau times f to the t times W to the t, which is equals to W to the t times 1 minus tau times f to the t. In other words, the proportion of the weight removed from the system at each time t is exactly proportional to the expected loss of the online algorithm. Now, using the fact that W to the 1 equals to n and using our lower bound on W to the t plus 1, we have 1 minus tau to the L mean to the t less than equals to W to the t plus 1, which is equals to W to the 1 times the multiplications of 1 minus tau times f to the t, where the multiplications starting with t equals to 1 to capital T, which is equals to n times the multiplications of 1 minus tau times f to the t, where t started from 1 to capital T. Taking logarithms, L mean to the t times ln of 1 minus tau is less than equals to ln n plus the summations of ln of 1 minus tau times f to the t, where t starting from 1 to t for the summation, which is less than equals to ln n minus the summations of tau times f to the t, where t starting from 1 to t, using the inequality that ln of 1 minus z is less than equals to minus z. So we take out the minus z term, which is equals to ln n minus tau times L RWM to the t, because by definition of f to the t. Therefore, L RWM to the t is less than equals to minus L mean to the t times ln of 1 minus tau over tau plus ln of n over tau, which is less than equals to 1 plus tau times L mean to the t plus ln of n over tau, using the inequality minus ln of 1 minus 0, which is less than equals to z plus z squared for those z which is between 0 and 1/2, which completes the proof.